So very good day to everybody. Once again, this is electromagnetic fields and waveguides, and this is the practical session. Okay, so we'll discuss about E H plane T. We already discussed about E plane T and H plane T in the last class. Okay, so we'll discuss the combination E H plane T, about the RatRace Junction, and about the directional couplers. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students and young researchers. Right. So in this class, we'll discuss about E H plane T, about the magic T junction, properties of E H plane T, symmetry property, scattering matrix of the magic T. Then we'll discuss about RatRace junction, directional coupler and directional coupler which is indicating pass. Then we discuss about the isolation property, okay, two-hole directional coupler and cavity glycerin. Okay, so at regular intervals I'll be giving you some short videos to discuss the knowledge in our topics. Right. E H plane T. We already discussed about E plane T and H plane T. So combination only E H plane T. So E H plane T, you have two simple waveguides, one parallel and other series. For example, in the E plane T, we have voltage type or maybe series type. Then we have H plane T, shunt or maybe current type. Okay, so both are combined. Okay, so here you will be having magic T or maybe hybrid or maybe 3 decibel coupler. Okay, so the arms, the two ports are nothing but the collinear ports. Okay, so port 1 and port 2 are nothing but collinear ports. Port 3, this port 3, you can call it to be the H arm or maybe the sum port or maybe the parallel port. And maybe port 4, you can call it as the E arm or maybe the difference port or maybe the series port. So 1 and 2 collinear arm, 3 H arm and 4 it is E arm. Okay. So this is actually sum port and this is actually difference port. So we'll have the connection diagram. Okay. So that is actually made by the side arms to the bidirectional waveguide in order to form the both parallel as well as series ports. So 1 and 2 collinear arm, 3 the sum port or maybe the H arm, 4 the difference port or maybe the E arm. So this is the magic T junction. Okay. So maybe if the signal of maybe equal phase and maybe a magnitude is actually sent to port 1 and then port 2, then output at the port 4 would be 0 and maybe output at port 3 will be sum of port 1 and then port 2. So maybe if the signal is actually sent to port 4, okay, the E arm, so power is divided between 1 and 2 but in the opposite phase. But there will be no output in the port 3. So S34 is equal to 0. Okay. So maybe if the signal you are feeding it at port 3, so power is divided between port 1 and 2 equally. No output at port 4. Okay, so S43 equal to 0. We know by the symmetry property S34 is same as S43. So that's 0. Okay. So maybe if the signal is fed to one of the collinear ports, so which means that no output at the other collinear port. Okay. So because the E arm, the electric field arm will be producing the phase delay and maybe H arm will be producing phase advance. Okay. So which means that S12 is same as S21 equal to 0. Okay. So we'll have the properties of the E H plane T. It can be defined by the 4 cross 4 matrix, which means that there are 4 inputs and 4 outputs. So S matrix can be given as S11, 12, 13, 14, 21, 22, 23, 24, 31, 32, 33, 34, 41, 42, 43, 44. Okay. So since it is having the H plane T, we already discussed this one. S23, this S23 is same as S13, same. Okay. And similar to the E plane T junction, S24 is 180 degree out of phase with S14. So that is the reason you get it as minus S14. Okay. So E arm as well as H arm port are isolated so that the other will not deliver the output if the input is actually applied to any one of them. Okay. So this can be given as S34 is same as S43, which is equal to 0. So we have like 4 equations now. Okay. So by symmetry property, we already know by the symmetry property of scattering matrix, Sij is equal to Sji, which means that S12 is same as S21, S13 is same as S31, S14 is same as S41. Similarly, S23, 32, 24, 42, 34, 43. That is by the symmetry property. Okay. So if the port 3 and maybe port 4 are perfectly matched to the junction, which means that this 3, 3 and 4, 4, that would be 0. Okay. So 3, 3 equal to 4, 4 equal to 0. So we are going to substitute all these values in the scattering matrix. 1, 1, 1, 2, 1, 3, 1, 4. 2, 1 is same as S12 by the symmetry property. Okay. S22. 2, 3 is same as 1, 3. We already discussed. 2, 4 is 180 degree out of phase. So it is minus S14. Then 3, 1 is same as 1, 3. 3, 2 is same as 1, 3. Same. 3, 3, 0. S33, 0. S34, S43, 0. Okay. Then S41 is same as S14. S42 is 180 degree out of phase. So minus S14. S43 already 0. S44, that is here it is actually 0. Okay. So this is this one. So you know by the unitary property, S multiplied by S conjugate equal to I. So this scattering matrix we are going to repeat here and conjugate equal to I. What is that I? Bir, 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 bir. Okay, diagonal 1. Remaining all, Hamasi 0. Remaining all 0. Okay. So we will go for this one. Row 1, column 1. Row 1, column 1. Okay. S11, S11 star. That is actually S11 modulus the whole square. Plus S12, S12 star. S12 the modulus the whole square. Plus S13, S13 modulus S13 the whole square. Okay. Then S14, S14. So S14 the modulus the whole square. So that is actually this one. We can substitute the values. So that's actually 1 plus S14 square. So we know that this value is actually 0. So that would be equal to 1. Okay. Then R2, C2. Okay. So S12, S12 star. Okay. S22, S22 star. That is actually S22 modulus the whole square. Plus S13. Okay. This one S13. Okay. So that is also S13 the whole square. Okay. So that is actually 1 plus S14 the whole square. So this is actually 0, which is equal to 1. Similarly, R3, C3. Okay. So S13, S13 star, which is actually modulus of S13 the whole square, plus S13, S13 star, modulus of S13 the whole square, plus 0 plus 0. Okay. Equal to 1. Okay. So similarly, R4, C4. S14, S14 star, which is actually S14 modulus the whole square, plus S14, S14 star, S14 modulus the whole square equal to 1. Okay. So we define 8, 9, 10 and 11 equation. Okay. So we can find out from the equation 10 and 11, we can find out 2S13 square equal to 1, or maybe S13 is equal to 1 by root 2. So similarly here, okay, 2S14 the whole square is equal to 1. So S14 is equal to 1 by root 2. So we can compare, this equation. So both, if you can see, okay, when you try to compare, both are similar. Okay. So S11 is same as S22. Okay. So you can substitute all these values from this S13, S14, S11, S22, everything you can substitute. Okay. We can have in the equation equal. Okay. So S11 square plus S12 square plus 1 by root 2 the whole square plus 1 by root 2 the whole square equal to 1. Okay. Or maybe S11 square plus S12 square plus, what is that ERM plus ERM? Bir. So this bir, if you take that side, 1 minus 1, it is actually 0. 1 minus 1, it is actually 0. Okay. So this one, S12 square, if you take that side, it will be the same. So S11 is equal to S22, which is equal to 0. Okay. So similarly, if you can see this equation 9, if you try to substitute, okay, so that would be equal to 1. Okay. So here if you can see S22 would be equal to 0. So because S11 is equal to S22. Okay. So that S22 is also 0. Okay. So we try to substitute all this one in the scattering matrix. Okay. 0, 0, 1 by 2, 1 by root 2. Everything you try to substitute. Okay. So B is nothing but the reflectance matrix. S is nothing but the scattering matrix. A is nothing but the incident matrix. Okay. So B, B1, B2, B3, B4. What is it? Yes, this is the scattering matrix. So here we will have, okay, A1, A2, A3, A4. Okay. So we understand that port 1 and 2 are actually perfectly matched to the junction. So since it's a port 4 junction, so whenever two ports are actually perfectly matched, the other two ports are also perfectly matched to the junction. Okay. So the junction where all the four ports are actually perfectly matched, you can call it as the magic T junction. Okay. So if you try to substitute, you will have the scattering matrix with this one. B is equal to S multiplied by A. So the applications, you can use the E H-plane junction to measure the impedance. So the null detector, which is actually connected to the E arm port, while maybe the microwave source, you are connected to the H arm port. So here the collinear ports together with the ports will be making the bridge, and maybe impedance measurement is actually done by balancing the bridge. Okay. So E H-plane T, you can use it in the duplexer. Okay. Duplexer means which is working both as a transmitter and maybe receiver using the single antenna. So here port 1 and port 2, we know that it's a collinear port. So they can be used as receiver and maybe transmitter where they are isolated. So isolated means they will not be interfering with each other. Okay. So antenna you are connecting to the E arm port, and maybe match load you are connecting to the H arm port. So that is providing no reflections. So there will be like transmission or maybe reception without any particular problem. So E H-plane T, you can also use it as a mixer, which means that E arm port you are connecting with the antenna and H arm port you are connecting with the local oscillator. Okay. So port 2 will be having the match load which has no reflections, and port 1 has a mixer circuit which will be getting half of the signal power and half of the oscillator power in order to produce the intermodal frequency. Okay. So in addition to these applications, you can use the E H-plane T junction in the microwave bridge, microwave discriminator, and so on. Okay. So port 1, port 2, port 3. Okay. So collinear arms, side arms, E field, H field. Okay. So that is how it goes. Then we move on to the second part of today's class, which is nothing but the RatRace junction. Okay. So the microwave device is actually used when there is actually need to combine two signals but with no phase difference and to avoid the signals with a path difference. So the normal 3-port T junction we will be using, and fourth port is actually added in order to make a RatRace junction. Okay. So all of these will be making the angular ring at the regular intervals. So regular intervals would be like lambda by 4, lambda by 4, lambda by 4 using the series or maybe parallel junction. So the mean circumference you will be having 1.5 lambda. Okay, that is nothing but 3 by 2 lambda. Okay. And each of the 4 ports are separated by lambda by 4, lambda by 4, lambda by 4. So total would be 3 lambda by 4. Okay. So that is how we will have the image of the RatRace junction. P1, P2, P3, P4. Lambda by 4, lambda by 4, lambda by 4, 3 lambda by 4. So we'll have case 1. Okay. So if the input power is actually applied at port 1, you are going to split it into 2 parts. One in the clockwise direction at the port 2 and maybe another in the anti-clockwise direction for the port 4. Port 3, no output. Okay. So the reason is that at port 2 and 4, the powers are going to combine in phase, whereas at port 3, cancellation occurs due to the lambda by 2 path difference. Then you have case 2. So if the input power is actually applied at the port 3, so power will be divided between 2 and 4. So no output at port 1. Case 3. 2 unequal signals are applied at port 1. So output would be proportional to the sum of the 2 input signals. So which is actually divided between 2 and then 4. So port 3 differential output is going to have because of the unequal signals. Okay. So this is the scattering matrix for the RatRace junction. If you can see Bir, Uj, same. Ikka, Tur, same. Okay. So 0, 0, 0, 0, S12, S32, S14, S34. Similarly here, S21, S41, null, null, S23, S43, null, null. Okay, 1, 2, 1, 3, 2, 4. Okay. So RatRace junction, you can actually combine the two signals, okay, and you can divide the signal into two halves also, okay. So you can also use directional coupler that is going to sample a small amount of microwave power for the measurement purpose. Maybe you can have power measurements including incident power, reflected power, VSWR, voltage source wave rectifier, okay, values and so on. So as I told you, directional coupler, it's actually a 4-port waveguide junction. We'll be having primary main waveguide and secondary auxiliary waveguide. Primary waveguide, secondary waveguide, 1, 2 primary waveguide, 3, 4 secondary waveguide. So here it will be going straight, here it will be splitting even. So combining, splitting. So directional coupler, you can actually couple, the microwave power, which can be either unidirectional or maybe bidirectional. Okay. So properties will be having as follows. All terminations are actually matched to the ports. So when the power travels from port 1 to port 2, some portion of it gets coupled to port 4 but not port 3. As it's a bidirectional coupler, so when the power travels from 2 to 1, some portion of it gets coupled to port 3 but not port 4. So if the power is actually incident through port 3, a portion of it is actually coupled to port 2 but not port 1. So that is how. Okay, if the power is incident at port 4, portion would be coupled with port 1 but not port 2. 1 and 3 are decoupled, same as 2 and 4. Okay, so the output at port 3 would be 0. Okay, so we'll have small amount of power called as the back power. Okay, that is actually observed at the port 3. So here we'll be having incident power, received power, back power, forward power, main waveguide, auxiliary waveguide. Okay, so PI, incident power at port 1, PR, received power at port 2, PF, forward power, forward coupled power at port 4, PB, back power at port 3. Okay, so from this only we will try to define the coupling factor C, that is actually ratio of the incident power to the forward power. So C, coupling factor 10 log PI, incident power divided by forward power in decibel. Directivity, it is actually the ratio of the forward power to the back power. Okay, so that is measured in decibel. So D is equal to 10 log PF by PB decibel. Then we'll have isolation. Okay, so it's nothing but the directive properties of the directional coupler. It is the ratio of the incident power to the back power. Just what you have combined both the coupling factor and the directivity. Okay, so 10 log PI divided by PB, incident power to the back power. So isolation is equal to coupling factor plus directivity, what we saw earlier. So both are. So two-hole directional coupler we'll be discussing. So it's actually a directional coupler with both the main as well as auxiliary waveguides. But it will be having two small holes that are common between them. So the holes are actually lambda g by 4 distance apart, and lambda g is nothing but the guided wavelength. Okay, so we will be having two-hole directional coupler, main waveguide, auxiliary waveguide. So this is actually guided wavelength lambda g by 4, PI, incident power, reflected power. Okay, so the two-hole directional coupler is actually designed in order to meet the ideal requirement of the directional coupler in order to avoid the back power. Okay, so some of the power while traveling between 1 and 2 escapes through the holes 1 and 2. So the magnitude of the power actually depends on the dimension of the holes. Leakage power at both the holes are in phase at the hole 2, adding up the power contributing to the forward power PF. So but however it is actually out of phase with hole 1, so which means that it's going to cancel each other and maybe preventing the back power to occur. Okay, so here the directivity of the two-hole directional coupler will generally improve. Okay, then we'll have waveguide joints. Okay, so as the waveguide system cannot be built in a single piece, so it's actually necessary to join different waveguides. So the joining can be done to prevent problems like reflection effect, standing wave, and maybe increasing the attenuation. Okay, so besides avoiding these irregularities, we should also, the waveguide joints should also take care of electric field as well as magnetic field patterns as well by not affecting them, by not impacting them. So there are many types of waveguide joints. We have bolted flange, flange joint, choke joint. So there are several examples. So finally, cavity glycerin. So generally for the generation and maybe amplification of microwaves, we'll use microwave tubes called as the glycerin. Okay. So generally we'll have glycerins as electron beams and maybe cavity resonators. Okay. So electron beams are generally provided from the source, so that will be emitting the light. Okay. And cavity glycerins are employed to, amplify the signals what you've got. So collector is present in order to collect that particular electrons. So the whole setup we can see here. Okay. Electron gun emitting. Okay. Cavity resonator. Okay. Then collector to collect the signals. So electrons emitted by the cathode are accelerated towards the first resonator. Okay. Collector at the end is at the same potential as the resonator, and generally the electrons have the constant speed in the gap between the cavity resonators. So initially the first resonator is supplied with a weak high frequency signal which has to be amplified. Okay. The signal will actually initiate the electromagnetic field inside the cavity. So the signal is actually passed through the coaxial cable as we saw here. So signal applied through the cavity resonator. So due to this field, the electrons that pass through the cavity resonator are actually modulated. Okay, so on arriving at the second resonator, the electrons are induced with the another electromotive force at the same frequency. So this field is actually strong enough in order to extract the larger signal from the second cavity.